All right, let's get you ready for your Computing for Medicine exam. Look, this test isn't about just memorizing a bunch of facts. It's really about understanding one big, central idea. How do we actually teach computers to speak the language of medicine? In this explainer, we are going to break down every single key concept, piece by piece, from word vectors all the way to transformers, so you can walk into that exam feeling totally prepared.
Okay, so here's our game plan. We'll start with the big picture of the exam itself. Then, we're diving deep into how we turn words into numbers a computer can crunch. After that, we'll get inside the amazing transformer architecture, connect it all to the specific language of medicine, and then we'll figure out how to tackle those big essay questions. And of course, we'll wrap it all up with a super focused revision blueprint.
First things first, let's decode this exam. We're going to focus on the one core principle that honestly connects almost every single question you're going to face.
This right here. This is the golden question. Everything we're about to cover, word vectors, transformers, all those clinical codes, it's all just a different attempt to answer this. So as we go through everything, just keep this question buzzing in the back of your mind. It's the thread that pulls it all together.
So let's get into our first major topic. You see, before a computer can even begin to understand language, we have a problem. We have to turn words into numbers. We have to turn language into math.
This is the bedrock of pretty much all modern natural language processing. The idea is actually kind of beautiful and simple. You shall know a word by the company it keeps, right? Words like doctor and physician, well, they tend to show up in really similar sentences surrounded by similar words. So it only makes sense that their numerical representations should end up being really, really close to each other.
Let's look at two of the most basic ways we can do this. Over on the left, you've got one-hot encoding. It gives every single word its own unique vector with just one 1 and all the rest are zeros. It's like having a giant control panel with a separate light switch for every word in the dictionary. Then on the right, there's bag of words. This one is way simpler. It just counts up the words in a sentence and smushes them into one summary vector. The key thing here, it totally ignores word order.
Okay, so what's the catch? Why don't we just use these simple methods? Well, the vectors they create are massive and mostly full of zeros, which is just not efficient. But the much bigger problem, the real deal breaker, is they have zero concept of meaning. To these models, the vector for doctor is just as different from physician as it is from the vector for apple. They just don't get the relationship.
And that brings us to word2vec, which is a really clever solution to this problem. This is a huge concept for your exam, and it comes in two main flavors. Think of SIBO as playing fill in the blank. It looks at the surrounding words, the context, to predict the word in the middle. Skipgram, on the other hand, does the exact opposite. It takes one word and tries to predict its neighbors. Now, Skipgram is a bit slower to train, but here's the key. It's way better at learning good, meaningful representations for rare words, which is a big deal.
So let's see how this actually works, because this is exactly the kind of thing you might have to do on the exam. If our target word is fox and we set a window size of 3, the model goes through and creates these training pairs. It learns by getting better and better at predicting that words like quick, brown, jumps, and over are very likely to be neighbors of the word fox. That's how it builds that semantic understanding.
Okay, so now we have a way to represent words as these dense, meaningful vectors. So what's next? Well, now we need to look at the architecture that completely changed the game for how computers understand them, the transformer.
So here's a wild thing about transformers. They process all the words in a sentence at the exact same time in parallel. This makes them incredibly fast, but it creates a new problem. The model has no idea what the word order is. That's where positional encoding comes in. We basically add a little bit of mathematical information, a signal, to each word's vector that tells the model its exact position in the sequence. And that is how it knows that dog chased cat is a completely different story from cat chased dog.
Now, don't let this formula scare you. It looks intense, but it's the absolute heart and soul of the transformer. Here's the gist. For every single word, the model generates 3 different vectors: a query, a key, and a value. Think of the query like the word asking a question. Hey, in this specific sentence, who am I and what should I pay attention to? It then compares its query to the key of every other word in the sentence to find a good match. That match gives it an attention score, which basically tells it how much focus to put on those other words when it's building its final understanding.
All right, so there are a few other key components that make this whole thing work, and you'll definitely see these pop up as multiple choice questions. The scaling factor? That's just a little math trick to keep the numbers stable so the calculations don't go haywire.
Residual connections are like little information highways or shortcuts that help the model train really deeply without forgetting what it learned in the earlier layers. This helps fight something called the vanishing gradient problem. Look-ahead masking is super important for tasks like translation. It stops the model from cheating by peeking at the answer. And finally, you've probably heard of BERT. It's one of the most famous models ever, and it's built using this powerful transformer architecture.
So let's connect all these powerful general models back to the very specific, highly structured world of medical language. And we're going to focus on something called SNOMED CT.
Okay, this is really important to get right. SNOMED is so much more than a dictionary. Think of it like a giant, intelligent Google Maps for all of medical knowledge. Every single concept, like myocardial infarction, gets its own unique ID. That ID is then linked to all the different ways we might talk about it, like the synonym heart attack. But here's the magic. It's also connected to other concepts through relationships, so it knows the finding site is the heart. It might know a causative agent. And this creates a massive, interconnected graph that a computer can actually use to reason about medicine.
Okay, let's switch gears and talk strategy. It's time to tackle those big essay questions. These aren't just about spitting back one fact. They're about you weaving together multiple concepts into a strong, coherent argument.
For that first long-form question, here's your blueprint. Seriously, structure your answer just like this. First, you state the problem. Transformers are language wizards, but they don't know a thing about medicine out of the box. Second, you propose the solution. We can inject that expert medical knowledge using a structured system like UMLS, the Unified Medical Language System. And finally, and this is where you get the top marks, you explain exactly how you would do it. You need to mention specific technical methods, like concept embedding or biasing the attention mechanism to pay more attention to known medical relationships.
And this is why it all matters. Don't forget this part. You have to connect all that technical detail back to the real-world clinical impact. The goal isn't just to build a fancy model. It's about building tools that actually help doctors make better, faster, and more reliable decisions. It's about cutting through ambiguous language and leveraging this huge web of medical knowledge to improve patient care.
Now, for the ethics essay. To get a great grade here, you need to show you understand more than just the tech. You have to understand the principles. If you ground your answer in a statement like this one, it shows the examiner you get the very real, very human element behind all this data.
So here's the absolute core of your argument for this essay. De-identified does not mean risk-free, not even close. You should explain the technical risk of re-identification, how you can combine seemingly anonymous data points like age, zip code, and hospital visit date, we call those quasi-identifiers, to figure out who someone is. Then you hit the obvious legal breach of the data use agreement. And now you should mention the new emerging risk that these incredibly powerful large language models could literally memorize and leak sensitive patient information from their training data. And always conclude with the only acceptable best practice. Use secure, access-controlled institutional servers for any and all patient data. Whew, okay, we have covered a lot of ground. So let's take a deep breath and quickly summarize the most critical ideas you need to have locked in for your final revision.
If you're short on time, this is your revision cheat sheet. Focus on these 4 pillars. 1. For word vectors, be crystal clear on the different goals of CBOW versus skipgram. 2. For transformers, don't just memorize the names of the parts, know what each component, attention, positional encoding, actually does. 3. For the medical context, remember that SNOMED and UMLS are what add the structured, factual knowledge that these general models are missing. And 4, for ethics, your North Star is always this: patient privacy is absolutely non-negotiable.
And I just want to leave you with one last thought. Remember that what you're learning here isn't just theory to pass an exam. These concepts, turning language into data, understanding context with transformers, structuring medical knowledge, these are the actual building blocks for the future of medicine. You're learning the skills that will redefine patient care. You're at the forefront of this change. Now, go ace that exam.